Hi, welcome. Today we're going to talk about ionic bonding. I know we started a little bit on this topic before the break, but I want to really have us have a full set of notes and a video on this so we can review. Before we start though, you will need two things: your periodic table handy and your ion sheet, which was handed out before the break. If you do not have that, go to the website and find it in the download section for your class. It's called Ion Sheet. Just download it, print it, so you can actually have it, or have it at least on your screen, so you can have it accessible for you to do the problems that we're going to be working on. All right? Okay. Let's go ahead and get started. Ionic bonding is actually the electrostatic attraction that occurs between ions of opposite charge. That means if you have a positive and negative charge and they come close together, that's what's going to be an electrostatic attraction. If you make chemicals that have positive and negative charges, chemical species, those will attract and form what is called an ionic bond. All right? Now, the most common type of ionic bond that you guys get to talk about at this point is what are called binary ionic bonds that are made from two elements, all right? Normally a metal and a non-metal, with the metal being the element that loses electrons because metals have a loosely held valence electrons, while non-metals will tend to instead take up the electrons because they have more tightly held electrons and they're closer to having a filled valence shell. So metals will want to lose the valence shell. Non-metals will want to gain in order to have a full valence shell. We can see then that this is the general configuration that we have here. It's basically the idea of the element that loses electrons is going to be the cation. The element that gains electrons is going to be what we call the anion. All right? And let's look at this example that I have here for you guys. If we have lithium and sulfur, we can see that if lithium loses one electron, it will become lithium plus 1. And if sodium gains 2 electrons, it will become the sulfide ion S negative 2 negative. How do we know how many electrons it's going to lose or gain? We look at where they are in the periodic table. All right, in this particular case, for elements, it's relatively straightforward. And if it's not, we always have our ion sheet to fall back on, which gives us a lot of information on this particular species. All right, so we have that we've made our lithium plus ion, and we've made our sulfide ion, our S negative 2. All right? Well, in order to make the compound, you have to remember that all compounds, all ionic compounds, are neutral. And so we're going to do the crisscross. We are going to take the charge of the positive ion and bring it down, the charge of the negative ion, and bring it down just a number. The charges themselves will cancel out, and we will come to make quite this compound, lithium sulfide. All right, and the lithium sulfide will have the formula Li2S. All right, and the name of it is lithium sulfide. Now, how do we come up with that name? I have a nice little reminder for you here. All right, when we are naming binary ionic compounds, we're going to have the name of the metal ion first, followed by the name of the non-metal anion. And the non-metal anion is named just like the non-metal, but the last syllable is replaced by the word "ide." So instead of oxygen, we have oxide. Instead of sulfur, we have sulfide. So we change that last little bit always. Carbon, carbide, phosphorus, phosphide, etc., etc. All right? And if we are starting from the starting materials element, and we're writing a chemical equation, we have to make sure that it's balanced. And so we want to make sure that we count. We have got 2 lithium ions in the starting materials. We got 1 sulfur ion in the starting materials. So we look at what we have in the product. We have 2 lithium ions in the product and 1 sulfur ion. So we need to include a 2 to make this a balanced equation. Make sure that when you're doing it, starting from the basic elements, you always balance your equations. Okay? So I'm going to ask you to try out this 4 little problems there. Remember that if we have elements that are diatomic or polyatomic in their elemental form, we do not worry about the charge. We do not worry about the number of atoms. We only make the monoatomic ions. So in the case of oxygen, in the case of bromine, and in the case of sulfur, we are going to make directly the ion that they make, not any other ions with subscripts underneath. The subscript comes when we do the crisscross, not before. All right? Give that a try. We talked about this in class. We gave you some more examples of that, so I want to make sure that you can finish this ones. But what I want to focus more on today is actually working with ionic compounds that are formed between polyatomic ions. These are ions that are formed or that are made through other different reactions. We will see how they're made when we look at, in particular, acid-base chemistry. But these ions, when they have more than one atom, they're called polyatomic ions, and they exist as a whole. So that entire structure will be attracted to an ion of the opposite charge. Just like in any other compound, the compound is going to be neutral, and so we can still use the crisscross to make our polyatomic ionic compounds. All right? So an example of a polyatomic compound, all right, ionic compound would be something like sodium carbonate, all right, or one that I have written for you down there is magnesium nitrate. So let's look at how magnesium nitrate is made, all right. If we take the name magnesium nitrate, all right, we know then, we can identify that there are two ions. I don't know why this is. There's two ions, the magnesium ion, which is Mg2+, and the nitrate ion, which is NO3 with one negative charge. How do we know again that nitrate is like that? We go to our ion sheet. You need to memorize those ions. The entire sheet is now going to be part of your vocabulary. So make sure that you start doing this. It is going to be important for the quizzes and tests that we have further on. All right, once you have your ions, what are you going to do? You're going to go ahead and do the usual crisscross. All right, the charge is going to go and be placed underneath. The charge over here, just a 1, is going to be placed underneath. So that would be a 1 for this one and a 2 for that one. But make sure you understand, we are not changing the structure of the ion. So we need 2 of that entire ion to be connected or bonded to the magnesium so we can actually get a neutral compound. And so we get the formula that I have written down here in black. Mg, and in parentheses, NO3, and outside the parentheses 2. And that is what is going to help us do this. Okay? So I want us to work on this example together, so I would suggest maybe pausing the video while you attempt to do ammonium sulfate, and then you can see me do that. All right? So take a moment, put the pause button, write what you think would be the formula for ammonium sulfate. All right, here I go. I'm going to show you a little bit about ammonium sulfate. The ions that we have involved there are the ammonium ion and the sulfate ion. And so what I'm going to do is I'm going to go crisscross. There's only a 1 there, so nothing that would change the structure. And then there's a 2 here, and I'm going to get 2 of that particular ion. So my actual compound would look like this. Notice that I have not changed how I write ammonium. It's still NH4. I'm not including the charge because when it's part of the entire ionic compound, the charges cancel each other out. It doesn't mean that the charge ceases to exist. It's just that because it's next to a negative, we do not experience the entire charge. All right? Hopefully you got that one right. Let's go ahead and move on and talk a little bit about the properties of ionic compounds. Ionic compounds are neutral. Well, of course, we have a positive and negative ion. and they will combine in such a way that you get a neutral compound. That is straightforward and something that we've been talking about all along. They're also crystalline. So if you let them solidify, the ions are going to organize themselves in such a way as to make what is called a crystal lattice, a repeating pattern that minimizes the repulsion between like ions and maximize the attractions between the opposite charged ions. All right? And you can see here we have two drawings, one that is much more densely packed to kind of show you really what the structure of an ion crystal looks like, and then one that's a little bit more loose so you can actually see it in 3 dimensions, how it actually works. Take your time, take a pause, and maybe look at it a little bit. You can see that there is an alternation of positive and negative charges throughout in every direction in all 3 dimensions. All right? Because of this crystalline structure, ionic compounds are also brittle, and you will see this. Let me tell you a little bit more about that. So if you have a compound and you have the pattern, that repeating pattern, you will see that we have positive, negative, positive, negative, positive, negative, and it repeats in all 3 dimensions. I only drew 2 dimensions to make it easier. All right? But brittle means that if you put a stress on it, it will break. If I come and I push down on this, I now have my positive next to the positive, and they will try to repel, and my negative next to the negative, and so they want to push each other away. All right? And if that repulsion is strong enough, what ends up happening is that our compound flies off, all right? And it breaks, and that's exactly why. If we had it like this, it would stay together, but if we modify the shape of the lattice, that causes the compound to break off and cleave, all right? So hopefully that explains the brittle part. Then let's just go ahead and talk about conductivity. Conductivity, again, is similar. We have our arrangement of positive and negative charges. In order to conduct electricity through an object, you have to have charges that move. In a metal, it's the electrons that are moving, but in an ionic compound, all right, it is those ions that are present that are going to be moving to carry electricity. Here's the thing. In the solid phase, those electrons, all right, those ions are not capable of moving because they are rigidly in place. But if you melt the compound, if you have it in the molten state, or if you put it into solution, if you dissolve it into water, those ions are free to move and move towards the positive end or the positive cathode electrode, or to the negative electrode, and to actually get some motion of that, and that carries electricity. So the motion of charged particles is what carries electricity across a substance. So to give you a little bit more of an idea, all right, we have it in the images here, but I want to show you. In the solid phase, you know, your atoms and electrons are not going to move in one direction or the other, all right, because we have both positive and negative that are together there. But if instead we have them independent, now the negative ions that are represented by the blue are going to be moving more towards this direction, bringing the negative charge in this side, and some of the positive ones will start moving over in this direction. Whoop, too far. All right, and that motion of ions towards one side or the other, depending on their charge, is what carries electricity across. And this will happen whether you are in solution or you are in the liquid phase or in the molten phase. All right? And finally, the last idea here is the idea of the fact that ionic compounds have high melting points. They have high melting points because they are attracted to each one of the other ions next to it. All right? And again, this ion over here, in order to melt, needs to be taken away. But in order to be taken away, you have to break the attraction that it has to all the other ions around this, and not just in 2 dimensions like we have there, but in all 3 dimensions. So to take this guy out and melt it, it's going to take a lot of energy. The more energy that it takes, the higher the melting point is going to be. So very straightforward. We have our properties of ionic compounds. All right. So for next class, I want you to attempt these problems. I have some problems there to write chemical formulas of ionic compounds, to write the names of these ionic compounds, and finally, and you can go back to check these equations, I have a little challenge question. These 2 compounds are very similar, and they both contain iron and the cyanide ion. How would you name them in such way to make sure that I don't write one when I mean the other one? Okay, so give that a try, and these notes are also available in just print format. You can have it in the PDF on the download page of the website, so just make sure that you take those down if you need to copy anything else. All right, I'll see you this week, and make sure you have all of these answers and the 4 little problems from earlier ready in your notebooks to check. All right, thank you. Bye.